Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study mappings or transformations of functions on complex variable. Earlier, we have studied functions of a complex variable, and now we shall draw graphs of these functions from z plane to w plane. Because if you consider function of a complex variable as f of z is equal to w, where z is x plus iy and w is equal to u plus iv, then z is function of two variable and w is also a function of two variable. To visualize a graph of the function in same plane, it becomes of four dimensional, and therefore it is difficult to visualize in one plane, and thus we shall draw two planes separately, z and w plane. That means we shall consider this as a z plane. As x and y, xy plane, and this we shall consider as w plane, that is uv, and a variable z or a point z which is x comma y or x plus iy will be transformed. Image of z is w, will be transformed to w, point w on uv plane. So this is a transformation or mapping from one plane, z plane to w plane. Now we shall consider some examples of these mappings. As first we shall have rotation, translation, rotation and reflection. See, translation, we shall consider examples of these mappings: translation, rotation and reflection. But for this we shall consider only one plane, and these are simple mappings and can be visualized in only single plane, z and w plane to be the same. First we shall have translation. And for example of translation, we shall consider, let w is equal to z plus 1. This is a transformation, or that means, so what is the z? Z is x plus iy, that is w is equal to x plus iy plus 1, or this means x plus 1 is real part plus iy is the imaginary part, and this plane, this mapping transforms the point z in one unit on the right, and therefore it is known as translation. This transformation translates z to one unit on the right, or shifts one unit on the right. So therefore it is known as translation. It is for example we have considered, and if you consider w is equal to z plus 2, then it will transform the point z to 2 unit on the right of z, and y will remain the same. See, for example, if you consider the graph, then this is in xy plane. We will we are considering the plane same, x z plane only, and one plane we are considering, not like this z plane and w plane separately, because these are certain simple mappings, and this is a point z having x coordinate as the coordinates as x y, and the image of this w, which is f of z, is z plus 1, and therefore z plus 1 is x plus 1 plus iy, and this point x the coordinate of z is x, is transformed to one unit on the right, that is x plus 1, and the corresponding point will be w now. W is x plus 1, the x coordinate will be x plus 1, y coordinate is same, and this is the transformation of z to w. So, it shifts or translates the point z to one unit on its right for this particular example, and therefore, this is an example of translation. Now, we shall consider example of rotation. For this, we shall consider the polar form of complex number, and we have z is equal to r e power I theta, complex form of polar form of complex number. And what is I we can write e to the power I into pi by 2 by Euler formula. E to the power I pi by 2 is cos pi by 2 plus I sin pi by 2, which is I, and we have seen this earlier. So, with the help of these two, consider the mapping. Consider a mapping. W is equal to I z, that is f of z is w, f of z is equal to w and is equal to I z, and I z, I we can write e power I into pi by 2. So, e power I pi by 2, and z we can write r into e power I theta, and here we can take see r is the common term, or we can write r separately, and this exponential term we can write as I into bracket pi by 2 plus theta, or theta plus pi by 2. So, this is image of f of z, that is I z, I into z, and now you see z is r e power I theta, or that is f of, or w is equal to f of z, and that is f of r e power I theta, and that is equal to r e power theta plus pi by 2. What is the change is happening here? Transformation is r remains the same, that is modulus of the complex number is the same, but the argument is increased by pi by 2. Here the argument is theta, here the argument is theta plus pi by 2, and therefore, the point, therefore, in this transformation a point z is equal to r theta is transformed or is mapped to a point w is equal to r theta plus pi by 2. Therefore, image of this point is, that is, it is rotated. So, image of the point z is a vector, or is a point obtained by rotating the radius vector through right angle about the origin and in anti-clockwise sense. Now, we can draw a figure for this. So this is xy plane, and we have shown earlier. Now you see, yes, and we have z. We shall show z like this, z, which is r theta. This is r and this angle is theta. And what is this point? Its image is r theta plus pi by 2. So that means the angle is further, this radius vector is rotated through right angle about origin, and thus we can consider this as the radius vector, this the same distance, and this angle is 90 degree. So this total angle will be theta plus pi by 2. Yes. So this is what is W. The image of this z point is W, obtained by rotating this radius vector through right angle. So thus this is r theta plus pi by 2, and this is an example of rotation. Now we shall consider example of reflection. Consider the mapping. W is equal to f of z is equal to z bar, and that is x minus iy. So this is a reflection. Then W is a reflection of z is equal to x comma y, or which is x plus iy in the real axis. That is it is a mirror image of z in the x axis, x, or that is the real axis. And see, it is easy to consider the figure. Suppose this is the point z, that is having coordinate x y, and we know z bar is x minus iy, complex conjugate. So its imaginary part is negative, and therefore this will be exactly the mirror image of this point in x axis, and this will be the point z bar having coordinates x and minus y. So thus this is an example of a reflection. And now we shall consider the next transformation as W is equal to z square. For this transformation, we shall draw z plane and W plane separately to visualize this, and it has two forms. One is Cartesian form, and another we shall consider is polar form. W is equal to z square, and we know z is x plus iy whole square, and earlier we have seen this expression or example how to simplify this, expand the square, and we shall get it as x square minus y square. I square plus y square is minus y square, that is real part, and the imaginary part is middle term I into 2xy. And if you put this in the form of u of xy plus I v of xy, then we have u is x square minus y square and v is 2x into y. Then we have u is equal to x square minus y square and v is equal to 2xy. We shall suppose this as equations 1. Now we will have two curves here, x square minus y square and in xy plane, and we shall see its image in w plane. Now consider first is as u is equal to c1. We shall consider x square minus y square is equal to c1. The equation x square minus y square is equal to c1, and we will assume c1 is greater than 0, and that will represent hyperbola, represents a hyperbola in xy plane. And so this is equation of hyperbola. So when c is greater than 0, it has two branches, right branch and left branch. Its axis is both x axis as the major axis. And now we will consider the image of this hyperbola. It has two branches, and we will write this equation. This equation will be u is equal to c1. So image of a point on right branch or right hand branch of this hyperbola will be a point on the line, on the vertical line. U is equal to c1 in uv plane. So we will draw a figure also for this transformation. W is equal to z square. There are two curves, u is equal to x square minus y square, and we will consider v is equal to 2xy. Both represents hyperbola. So this will be see, this is hyperbola x square minus y square is equal to c1. c1 we have assumed as greater than 0. This is points c1, and here it will be minus c1. Two branches will be there of this hyperbola, and it will be mapped. This is z plane, x, y, and we will consider w plane here. U v, and the line this every point on this hyperbola, as point moves from upward, then that point lies on this line u is equal to c1. So this is u is equal to c1, the line, this c1 point. This is the for the first curve. And now we shall consider the second. So image of a point on right hand branch of this hyperbola, or each we shall, instead of right hand, for the left hand also, but if the point moves downward, then the image will be image of this, both the points will move upward. As the point on the right branch point moves upward, and on the left branch point moves downward, but the image of both these points on these both the branches will be on this line u is equal to c1, because we have considered this as u, and x square minus y square e is equal to c1 is same as u is equal to c1, because this is u. And now see, in image of a point on both branches, we may consider right hand branch always as well as on both branches of this hyperbola will be a point on the vertical line u is equal to c1. Now, what happens for this next? Let this v is equal to c2, that is 2xy is equal to c2. Again we shall assume c2 is greater than 0. Then it is also a hyperbola and a point on this hyperbola. So, therefore, every point on this hyperbola, or if you consider c2 is not fixed, then it will be any hyperbola. On a hyperbola 2xy is equal to c2 has image on the horizontal line, because v is equal to c2 is a line which is parallel to u axis, and u is equal to c1 is a line parallel to v axis, that we know, has image on the horizontal line v is equal to c2. So, and that line can be shown like this. First we shall show this parabola. It has again two branches, and this is a rectangular parabola. So, we shall show the image by a broken line. And it lies in the first quadrant and in the third quadrant. So this is the parabola x square minus y square is equal to c1, and this is not parabola but hyperbola, and this is the hyperbola x square 2xy is equal to c2, and its image is v is equal to c2, and that we can show like this. This line is v is equal to c2, and thus this is the transformation of w is equal to z square. W is equal to z square in from z plane to w plane. It has two curves, u is x square minus y square, that is x square minus y square is equal to c1. c1 can be taken as any constant real number, and that represents hyperbola, and these two hyperbola will be mapped on this vertical line u is equal to c1, and this will again represent hyperbola. This we have shown by a dotted line, and every point on this hyperbola will be mapped, and it is easy to check because v is equal to c2 is the equation, that is 2xy is equal to v is equal to 2xy, and therefore v is equal to c2 is the image of this hyperbola, 2xy is equal to c2, and thus this is the Cartesian form of the transformation w is equal to z square. Now, to consider the polar form, it is easy. Second, polar form. We have z is r e power I theta. Now, the transformation is w is equal to z square, and that is r e power I theta whole square, or this is equal to r square e power I into 2 theta, and that we shall denote by rho e power I into phi. So, this is W, where rho is r square and theta is phi is 2 theta, and this shows that the point Z is transformed in this form, where the what is the change? The change in radius vector is becomes square. So, it is we have the radius vector is squared, and what about the argument phi becomes double. So, therefore, image of a point Z is equal to r e power I theta is the point is a point W, or is the point W whose modulus is r square and argument is phi is doubled, argument phi is double of theta or twice of theta, and this can be shown in figure like this. I shall draw a figure here. So, we shall show this as W plane, this as Z plane x, and Z is say this point, or suppose this is Z and coordinates are r theta, that means polar coordinates r theta, and this is r and this is theta. What is its image is the angle gets doubled, or if you consider this as theta, then we have to take the radius as r square, or if you consider this particular point Z as r naught e power I theta, and its image W will have the square of r naught, modulus is r naught square, and this as r naught. So, this is the point r naught, and now it is a square. We shall show the square here. Suppose this is square of r naught. This is the same plane x y, and but we are showing in separately, and the angle theta becomes 2 theta. So, if this is 2 theta, and this vector is r naught square. So, this is the image of Z, and that is r naught square 2 theta. And in this mapping, the first, if theta is pi by 2, then that vector will be mapped to the entire first quadrant and second quadrant. So, in this way we have seen how a point W, how a mapping W is equal to Z square transforms a point in one plane to a point on other plane. So, and we have seen the two forms, Cartesian and polar form of this transformation. I hope you will understand this. Thank you for watching the lecture.